sir.
Okay. Good. So let us start
Yes.
our discussion today. So in the last class, we have been discussing about this Dijkstra's algorithm, and so, I will just go over the Dijkstra's algorithm today in the rest of the class. Okay, and then I mean I've gone over the Dijkstra's algorithm already, but I will spend some more time on the Dijkstra's algorithm, and yeah, that will be all that I will be doing before the midterm.
So, sir,
Yeah,
regarding assignment, I have one question.
yeah.
For in question number 3, it is has been asked that design a linear time algorithm that given a connected unrelated graph, G decides whether there is an edge that if we remove it from G, whether leaving it will it be connected or not? So, is this same as finding whether there is a cycle in the graph?
No, no. For example, you can have a what is called a bridge. You can have something what is called a bridge of in the graph. So let me see if I can.
No, it is asked that whether there is an edge after removing it.
Yes,
After removing it, G is still connected.
yes.
So,
One second. Can you see my screen? Right now? No.
No, sir.
Just one second. Can you see my screen?
It's loading.
Okay. And you can hear me at least, right?
Yes.
Something is very weird today. I understand. It's still loading or is not yet come?
Yes, sir. It's loading.
Yeah, I don't know. Why am I not being able to connect from my? Just 1 second. Let me just quickly go back and try to see if I can do something else. You are sharing screen. That's what is being told. But it still says you are loading, right?
Yes, sir.
Oh, some issue is there because of my. Something is there. I don't understand this. Oh God. Just 1 second. So maybe I will try it out. Can you hear me now? Hello?
Yes, sir. Yes, sir. But it's echoing. Little echoing.
It's still echoing?
No, no, no. Not now.
Something is very weird because I have no idea how to connect my iPad to that. Somehow my iPad is not connected.
Sir, I think
Yeah. Maybe it's something related to my iPad, only I can understand this. Hello. Yeah, so let's continue here. Let me restart my iPad if that helps. Yeah, so coming back to the question that was asked, so if you can come up with an graph, okay, where there is a, so what happens, when can a graph be such that if I remove an edge, the graph becomes disconnected? So such a graph edge is called a bridge. So imagine a graph which is basically two cycles connected by a single edge, right? Hello, can you hear me?
Yes, sir.
Yeah, so somebody
sir.
says design a linear algorithm that given a connected directed
Yes,
graph.
sir, I posted the question.
Oh, you posted the question, that is fine, but I mean, do you so that is nothing to do with the cycle, you understand that or no?
I mean, removing an edge, but after removing an edge, the graph is still connected. I mean, if there is a cycle, then at least we can remove one edge and then also the graph will be connected. Right?
Yes, they can use one edge, but there maybe there is some a graph might have a cycle, and yet there might be an edge. If you remove that, the graph is still disconnected.
It is asking whether it will be connected, whether it is still connected or not.
Okay. Do you have a pen and paper with you in front of you? Hello. Do you have a pen and paper, Ujjwal?
Yes, sir.
Okay. Now draw a graph for me. Okay. Two cycles. Draw two cycles. Okay. And now draw an edge between those two cycles. Any two vertices of the cycle. Hello.
Yes, sir.
Yeah. Now, in this graph, what do you think? This graph has a cycle?
Yes, sir.
Okay. But does this graph has an edge such that if you remove that edge, this graph becomes disconnected?
Yes.
Okay. So this such a graph we have to find out. Goal is to find out whether there exists a edge that satisfies that is such that if you remove that edge, the graph becomes disconnected.
So we need to write the algorithm to find the bridge, right?
Yes. You have to come up with an algorithm to find the bridge.
And sir, regarding proof of correctness for this kind of graph algorithms, where should we read?
Should you read? Read the books. Have you read the books? Have you read any book about
Yes, sir,
have you read the proof of the Dijkstra's algorithm?
I was looking for this information.
Yeah, any book will have lots of graph algorithms and the proof will be there. The proof of the topological sort, the proof of the Dijkstra's algorithm. We will be going over some of them in this class. In today, we will be going over not some of them. We'll be going over the Dijkstra's algorithm, the proof of that in the class today. But otherwise, you should look at the book.
Sir,
Yeah.
one doubt regarding BFS algorithms.
Yeah.
Like while inputting the graph with the start vertex, like do we have any restriction over the start vertex?
Do you have any restriction over the start vertex? What?
Yeah, start.
Oh no, you can. I mean, that is given as a input.
Yes, sir. Yeah. Like what about if I give a vertex with out degree as a start vertex?
Yes.
So we won't get any BFS tree for that, right?
Then you will not get a BFS tree. It will just be one vertex, single vertex.
Yeah, yes. Sir.
Yes, that is true.
Oh.
If each
Uh,
start vertex has no out degree, then that will be a empty. That the BFS tree will be empty graph.
but like, then how do we decide, given a graph, whether it is connected or not? We need to
Okay,
have
so
some.
first of all, if you are talking about an undirected graph, then it doesn't matter.
No,
where
yeah,
you start.
no, directed.
If you have a directed graph, then the definition of connected is already a bit complicated, right? What do you mean by a definition? What do you mean by a graph is connected or not?
Oh,
What is the definition of a directed graph being connected?
a strongly connected and weakly connected.
So strongly connected. So if you want to take a strongly connected, that means from every vertex you reach every vertex. You can start from any
Yeah.
vertex and do a DFS. Okay. If you reach every vertex, that means you know that every vertex is editable from that graph.
Okay.
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 If that is not the case, then it was then you know that is not possible. That is not possible, right?
So strongly connected is not true, but we can't say anything about weakly connected.
What is weakly connected? Tell me the definition of weakly connected.
So sorry.
What is the definition of weakly connected?
As in, so given two vertices, there might be path between in one direction only.
Okay, so if you want to check whether there is a direct path from U to V, start a DFS from U and see whether you reach V or not.
Okay. But we have to worry about all such pairs, right?
Exactly. I am asking, what are you trying to check?
Weakly connected.
What do you mean weakly connected? For every pair, whether there is a path from U to V or V to U? Is this what you're trying to check?
Yeah.
Okay, in that case, you have to run from possibly many of them.
Okay.
Okay. I mean, definition of connectedness. You have to find out what is it that you want to solve. If you want to solve strongly connected, then that means something. By the way, just running DFS once. So if you to check a graph is strongly connected or not, just running it once is not good enough.
Okay, sir.
What, you understand why?
Yes, sir.
If you run it from a particular vertex, you say you reach all the vertices. All that you will end up proving that.
Like, if we won't meet any vertex, then there won't be.
You will end up proving that
because both the path needs to be there, right?
Sorry.
Like, if we run once with any vertex, if we won't, if the BFS tree doesn't cover entire vertex set, then there won't be a path between them, right?
There won't be a path between. I mean, no. So if you start from a vertex, right, or a BFS, and you say you reach every vertex, all it will say is that there is a path from you to every other vertex. But that doesn't prove that there is a path from every other vertex to you.
Yes.
Okay. So depending on what you want to prove, you have to apply that.
Okay, sir.
Okay. Is it fine?
So,
yeah.
Not connected using this, strongly not connected using this algorithm, whereas we won't be able to prove whether it is. Yeah. Yes.
Okay.
Hello.
Yeah.
Hello.
Can you hear me?
Sir, yes, sir. Yes. Sir, in question number 3, the same question which was asked before, this finding that you told that we have to find a bridge.
Yeah.
So in sir assignment, it is written that we have to check whether there is an edge after removing which it remains connected.
Yes.
So the example that you gave, in that we can remove one edge from any of the cycle.
No, I did not give you that example.
Sir, you gave that two cycles which are connected by
I did give her that cycle, but I did not say that statement. Okay, so it's important that you understand that what are the various things that are there. Okay, so what I told you is that give a graph, draw the graph which is a two cycles and connected by a single edge. So say this is one graph. You can see my thing now. Can you
Yes,
see my
sir.
screen?
Yes.
Okay. Consider this graph. Does this graph has a cycle? Mayank, does it have a cycle or not?
Yes.
Yes, sir.
Okay. Does this have an edge that if removed, the graph becomes disconnected?
So in the question it is written, it remains connected.
Okay, what is the opposite of that? Oh, so what was the question actually? Sorry, so maybe I made a mistake. Maybe I'm thinking of.
Sir, I wrote it in the chat.
Let me just
I
see the
copy
chat.
and pasted.
Whether there exists an edge you can remove while still leaving G connected. Oh, okay. So in that case, this has to be a, yeah. Okay, sorry. Okay. I made a mistake. Yeah. So whatever is written there is whether the graph has a. Actually, this okay. The idea was actually to come up with a different one to given a connected undirected graph to decide whether for every edge you can for every edge you can remove the even after remove that edge the graph has been connected or not. But okay, yeah, whatever has been given right now, it boils down to checking whether there is a cycle or not. You're right. Yeah. So how do you check it? How whether there is a cycle or not?
So using backage.
Sorry.
By detecting whether there is a backage or not. In
Whether there is a
BFS.
backage or not, or yeah, I mean, yeah, whether there is there is a non-tree edge or not. There are a lot of ways of in which you can do it. Is it fine?
Yes, sir.
Any other questions? Okay. So Adai, so you guys got my my message in the classroom and all that there is an exam on Thursday, next Thursday at 2:30 p.m. right?
Yes, sir.
Okay. I will tell you the more details, but basic thing is that at 2:30 you will be able to download the question paper from the classroom, Google Classroom. You are supposed to solve it, okay? And after you solve it, you take a photo of your answers and upload it in Google Classroom. Now, if you write it, irrespective of whether you write it in pen and paper or in computer or whatever, you are requested to write one question in one page and kind of arrange the papers in order of the question numbers. The other thing is, yeah, please write it in a more clear way so that it is easy to understand whatever you guys are writing, because correcting papers online is very hard. And the other thing is that the Zoom chat will be on that day continuously for that duration of the class of the exam. Either me or one of the TAs will be there always, and you can send your doubts in messages. Okay, you send your doubts as messages to me. Okay, try not to send it to everyone. Try to send it to only a private message to me, and we can chat. Is it fine? More or less? Hello?
Sounds good, sir. Sounds good.
Oh, sorry.
Yes, sir.
Okay, so let me go to the Dijkstra stuff today. So I will first of all shut down my. Let me share my screen from a different. Okay, so in the Dijkstra's algorithm, so then this is what we were doing in the last class, and the main idea was that you want to find a shortest path from between two vertices. Here we want to find the shortest path from G to A, and the Dijkstra's algorithm basically does what is called a single source shortest path. So that means it would go and find out the shortest path from G to every other vertex in that path. Okay. Fine. Now, now the main idea is that what we will be doing always is that we will be trying to maintain a collection of vertices for which we would have solved the question. So we will have finished the total, the final, the small, the shortest distance from G to every other vertex. So right now, for example, here, what we start with is a set of these vertices here, and currently whatever we are knowing. So currently what we know is the shortest distance from G to any of the vertices, A, B, C, D, E, F, any of the vertices is infinity, because we have no idea about anything, whether even it is reachable or not, we don't know, right? So G is the only vertex for which we of course certainly know that you can reach G from G with 0. See, here we will always maintain, what we will do is that we will be, as we progress in the algorithm, we will update the value, and at any point of time we will keep say the one here right below E. It will always maintain the current known shortest path from G to E through all the vertices that has already been explored. Not explored, has been already been finished exploring completely. And we will also maintain from which of those explored vertex do I reach. So let's see one example. So we start with, first of all, we know that G is there. So G is of course explored. As soon as G is explored, okay, so we know that G has two edges. There's edges to E and F. Edges to E and F. Okay, so that means look at E. So E before this was having infinity, right? But now, once I know that G is explored, I look at the edges of G, out degree of G, and I find out that, okay, E can be reached from G, and the cost of reaching E from G is 0 plus 9 is 9. Since 9 is less than infinity, I update the current known distance of G to E to 9, and I maintain that since I have been updating it thanks to G, I will maintain this G. It will be important for us to maintain this. Similarly for F, okay. Similarly for F, we realize that at this point when G is explored, the shortest distance from G to F is 11, and that also goes through G. Now at this point, right, at this point in this array, we know that there are this A, B, C, D, E, F. Hello.
Yes, sir.
Was I off for some time?
Yeah, the like your voice stopped suddenly and the screen is off right now, sir.
Can you see now?
Yes, sir.
Okay. So at that time, I see that between A, B, C, D, E, F, the lowest distance is for E, which is at 9, right? So that means I will now kind of declare that E is something I have completely figured out. E is completely explored, and I will say that the shortest distance from G to E is indeed 9. Okay. And once I kind of say that, what do I have to do? I will say that, okay, E is now explored. And at that time, all the outintegers of E, which is namely B, C, and D, for those vertices, I might have to update the value. For example, say C, what will it be now? If E has been explored, at that time, E's distance is 9. So if I consider the distance of C from E through E, it would be 9 plus 1, 10, right? And the distance will be through E. And so I will update the infinity in C to 10, E. And similarly for I will do it for B and D. Okay. So at any point of time, this is what I will do. Among the set of, so I will always maintain a set of vertices that I have already explored. For them, we will be knowing all the set of distances, all the minimum distances. Now, for all other vertices, I would be maintaining the cost of the shortest path from G to that vertex, passing only through the explored edges. Note that, for example, A is not even there is no path from G to A that only passes through these red edges, G and D. Therefore, A is currently unreachable from G, according to my distribution. Similarly, say you can see D. Right now, the only path from G to D via the explored edges is G, E, and D. It is 18, and that is what is stored here. If you can quickly look at this graph and you realize that the shortest path from G to D is not 18. It is in fact 17 going through F. But note that F is not explored completely, right? So the edges, vertices that are in the second half, you can think of, they are all the explored. So at any point of time, the one on the top array maintains the cost of the minimum path from G to that vertex, going through only those set of vertices that has been explored. Okay, that is the main idea. And at any point of time, and so about any recurrence or something, any loop, we will be looking at this set of vertices that has not been explored, and among them choose the vertex with the minimum cost and consider that one as explored and then update it. For example, here the minimum cost is 10, which is C. So we will say, oh, now I know that from G, the minimum cost to pass to C is 10. I will make C to be completely explored. And once I make C to be completely explored, I will have to look at all its neighbors, out neighbors. So B will be an out neighbor of C, and the path from, C will be reachable from 9, 10, right? That's what it's basically this is saying. And if I have to go from C to B, then B has to be reachable from 10 plus 9, which is 19. But 19 is bigger than E, bigger than 18, which is how this is done. So I will not be updating the shortest path. Okay. So I will be doing this one, and although I have made C to be completely explored, B I should have checked. I have checked, but it has not been updated. It is still having 18E, meaning it B still says that the shortest path from G to B is via E, and it is 18, not via C, via E. Again, at this point, which is the shortest of these two, of these three? It is 11. So I will update, I will make F to be completely explored. And at that time, I would be updating all its neighbors. Now see the neighbors again, there are two neighbors, E and D. Now E is not even, I mean, E is done. So E doesn't have to be updated. All that has to be updated is D. And yeah, so what if F gets explored, then the shortest path through F will be 11, which is whatever is here, plus 6, which is 17. If 17 is less than 18, it should be updated to D. So let's see. And this is what will happen. D gets updated. Now at this point, I would say that okay, now minimum of them is D. And at this point, I should update the edges, all the out neighbors. A gets updated. A for the first time becomes reachable from G via the red or explored vertices, and the cost is 22. B is also an out neighbor of D, but if I go through D, then the cost is 26, which is much more than 18, which is currently the known path from B to G to B, and that is why. So I don't update B, but I mean I have to check it. And now I take B, and at that time, of course, A has to also be updated, but A is like too costly because 18 plus 7 is 25, which is more than 22. And finally, I will put A. So the final thing will be this. The algorithm will be that here I will be done, and this is how will be stored. Okay. Now, what is the usefulness of this storing? Okay, not only I know the shortest path from G to everywhere, like G to A is 22, but if you ask me, can you find out the path, not just the cost of the path? Yes. You want me to find out the shortest path from G to A? Okay, it is 22 and it passes through D. So A to D. Now, how from D, where should I go? Look at D. D to F. Okay, D to F. And from F, okay, F to G. Okay, G. So you can do a back tracing of this path. So D, A to D, D to F, F to G. I have been able to find out the path from G to A this way. Okay, so this is basically the algorithm that we did in the example. And if I have to tell you the pseudocode is exactly whatever has been written there. Okay, we start with that every vertex have distance infinity. Then I initialize by saying that okay, consider the source vertex to have distance 0, and Q be a set that has been set to be set of all vertices. Now, while the set of all vertices is non-zero, what you take is that you take a vertex Q, which is the shortest vertex in the set Q. So Q is the set of unexplored vertices or not completely explored vertices. Okay, they are the vertices which have not been completely finished with, or for which we don't know exactly the shortest path between G to that vertex. And we would be right, and we would be taking that vertex, remove that vertex from Q. That means by definition, I am saying that okay, now that vertex becomes explored, and we will update all the neighbors of U, out neighbors of U. How? I would say that for all the out neighbors of U, they are already storing something. The dist always stores the shortest path between U, between the start vertex to that vertex V, right? Via all the explored paths, explored vertices. So D of V will become dist of V, minimum of dist of V, whichever was the thing initially. And if so now that U has been newly explored completely, I can have a path via U and one step forward. So dist of U plus the cost of that edge. and I update the distance of. And okay, I have not told you what to store, but at this point we can also output or store the cost of u or dist of u here will be the actually shortest distance of u, right? And this place, that's what I just now told, that you can maintain this g and all, they can be updated over here. So is this algorithm clear?
Yes, sir.
Okay. If the algorithm is clear, there are two very important questions over here. Number one, why is this algorithm correct? Can somebody kind of give me an idea? If I have to ask you, prove the correctness of the Dijkstra's algorithm, what will you do? Akash Kumar Gupta,
Yes, sir.
do you have any idea how we can try to prove the correctness of this algorithm?
No, sir.
Okay. Were you there in the last class?
Yes, I was here.
Okay.
I
But you
attended the
just
last
cared
class
about
too.
looking up the book or something after that, right? Okay. Avanish Kumar,
Yes, sir.
do you have any? Can you want to take a shot at how to prove this correctness of this algorithm? No.
Sir,
right?
we can see that
Yeah, well,
we can use a loop invariant in this.
yeah. What is the loop invariant?
Sir,
Actually, you are right. There is two loop invariants here. Okay, and actually there is two loop invariants here. Right? Can somebody say which are the two loop invariants? I'm doing two things here, important things every loop, right? I'm removing a vertex from Q. It means that I'm saying that Q is getting explored. I'm done with Q. I know the value of shortest path from the start vertex to the vertex U that I have removed from Q. That's the first thing. And the second thing is that I'm updating the distance at all these neighbors. But what am I storing? What is the thing that I'm storing in this thing? Mayank Devra,
Yes, sir.
you have any idea?
Sir, the first loop invariant can be that distance when we remove the vertex. At that time, the shortest path distance will be whatever is stored in dist of u.
Very good. Very good. That is the first loop invariant. That when I am that for all the vertices that are not in the queue, the distance value that is stored at that time, or distance value that is there, that is the shortest distance. Okay, so that is one loop invariant. And what is the other one?
So the other one I am trying.
Hmm?
Other one I am trying to figure out.
Okay. Shubit Das, are you there? Shubit Das. Okay, is appeared. Surachit Sarkar. Surachit,
Yes, sir.
yes, you have some idea?
Sir, actually I understood, but it will be difficult for me.
Okay.
It will take some time.
Umar Reddy.
Yes, I'm here, sir.
I mean, the
Yeah, so do you
minimum
have any
condition
idea?
is
Yeah.
I mean the minimum of a distance u comma distance of u plus w of u comma v. This one is another loop invariant, right?
Which is the loop invariant we are talking about. Loop invariant is something that remains same in the loop of the whole thing. By the way, whatever the loop invariant is, I have told it multiple times when I was explaining this algorithm. So it's not something new. What is it that we are storing in that distance thing? If we go back one step, what is it
We're
that
storing the minimum distance
minimum distance of what?
from the source,
We are always storing the
from
minimum
the source
distance of
vertex.
Are we
Yes,
always storing the
from the
minimum?
minimum distance.
Complete your
Min-
sentence.
We are storing the minimum distance from source vertex for a particular whenever we are traversing any particular vertex, we are updating the current distance, that is that initially was set as infinity.
So for example,
So
here,
that actually we are
what
changing
is
it to
yeah? So this is 18 here. Is this the minimum distance from the source to D? Is this the minimum distance from the source to
that
D?
is the current minimum.
What is it? What do you mean by current minimum?
Hello,
Yeah, what do you mean by current minimum? Can you explain?
that is the current minimum, sir.
What is the? What do you mean by current minimum?
Current minimum means the like already the vertex that we have already covered. Through that vertex, this distance is minimum.
Right. So that is the other loop invariant. That there are two loop invariants here. Number one is what Mayank told, that any vertex that is not in Q, for them the distance that is stored.
Your voice is breaking, sir.
Oh, sorry. Can you hear me now? Hello, can you hear me now?
Your voice. Yes, sir, but it's breaking in the mid sometimes.
Is it breaking now?
No, not now.
Okay. So the two in loop invariants are basically, one of them is saying that for all the vertices not in Q, okay, the shortest the value in the dist is the shortest distance from G, from the source vertex to that vertex. Okay. So maybe I can just write it down here, but since I'm using a very weird setup today, so it will take me some time. Hello, can you hear me? Hello, can you hear me?
Yes, sir. Yes, sir. You are audible.
Yes, sir.
Yes. Come on. Just one second. Yeah. Can you see my screen? Can you see my screen?
Yeah. Yes, sir.
Yes, sir. Yes, sir.
Yeah. So the two loop invariants. Okay. The loop invariants. Number one, for all U not in Q, okay, distance of U, dist of U is the shortest distance from S, source versus S, to U. Okay, so this is the source vertex. S to U. And the second one is that for all V in Q, dist of V is the shortest distance from S to V using only vertices in V minus Q. Okay. So these are the two loop invariants. The number one, the shortest distance. So if you is in not in the queue, then that is the shortest distance. And if it is in the queue, then the shortest distance is the it is the shortest distance by where only the vertices in V minus Q is used. And now, how do you prove the two loop invariants? Is the two loop invariants clear? Akash Kumar Gupta?
Yes, sir.
Yeah. Is it clear?
Yes, sir.
Okay. Avanish Kumar?
Yes, sir, clear.
Excellent. Now, can somebody try to prove it? Swarnalipa, do you have any idea how to prove this one? Prove the loop invariants?
Well,
So how do you prove it?
okay, so can you please show me the algorithm, sir?
Exactly where things are complicated because
Okay, sorry. Okay, it's written in my copy. Okay.
okay, because I'm using two devices. So one has the algorithm slides, one is the
Oh, okay, sir. Okay. Yeah. So whenever to prove the first one, I am taking the source vertex and then okay. So whenever I am removing a vertex from the queue, in that case, what to say? I mean, whenever I am removing, I am taking the for
You're
each
taking-
vertex for each. Sorry. What, sir?
you are taking the vertex which has the lowest minimum distance
Minimum
among all
distance.
the vertices. Yeah,
Yes.
that is you are doing. But
Yes.
how is that helping to maintain this?
Because, sir, whenever we are moving to some other vertex, in that case, we are calculating the distance with the help of this distance only. I mean to say, we are taking the minimum of all the distances. I mean, if U is the vertex, then we are taking the neighbors of U, and then we are calculating the minimum of all those distances.
So that is for this one. But when you are removing that U, okay, that
Yeah.
so consider the time when U is removed from Q. Okay, so U is at that time the minimum distance, right?
Okay. Yes.
At that time the loop invariant is there. Okay, till that time this is all satisfied, right?
Yeah.
I mean, it's the induction kind of stuff, right? At some point of time, all of them are satisfied. But now
Yes.
consider the time when U is being removed from Q. So U is at that time the minimum the vertex with the minimum distance.
Yes, it is.
Why is that distance the perfect distance? Why is this the shortest distance from S to U?
Because that distance is also calculated by taking the minimum of all the.
No, but that is S is only those which uses the vertices in this. It's a two different thing, right?
Yeah.
Distance in general, if you assume the loop invariant, right?
Yeah.
The distance is storing all the shortest path among all the paths that only uses V minus Q.
Yeah, the vertices which are removed already.
All the vertices are removed already. Now, when I'm removing U, a new vertex is being removed.
Yes.
Why is it that there cannot be any other path which is shorter than what uses only those vertices which are removed?
Sorry, sir, can you please repeat the question?
So do you
Hello?
understand that this distance u, that distance v is not necessarily the shortest path in the from S to u that is being
Yeah,
shown?
no, because in the next step, whenever we are calculating, we are taking the other neighbors. Yes. So in that case, I can get some distance which is lesser than, I mean,
I mean, what is being stored in dist of v? Dist of v is in general storing the shortest path between shortest distance between S to v, but only using the vertices in
in V
only
minus
the
Q.
vertices that have been removed. This is important. This is very, very important fact, right?
Yes, yes.
So this is not necessarily the shortest path from S to V.
Yeah, yeah.
There can be shorter paths from S to V that uses some other vertices that are in the queue right now.
In the Q, yes.
Then why is it that when I'm removing a vertex, why suddenly I'm claiming that that distance now becomes the shortest distance from S to U?
Because I haven't yet seen the other vertices. I have only.
Yeah, but it might be that I'm wrong, nah?
Yeah, yeah. I mean, okay, so.
So because we
No,
have
but.
covered all.
Sorry, sir. Actually, from S to U, whenever we are considering from S to U, then we have already. We have already seen the other. We have already. To come to you, we have already covered the vertices which are.
Okay, so do you think, Swarnalipap,
Yeah.
if we had not taken the vertex U, which is the minimum one among all the distances, would the same thing work? Would the algorithm still hold?
No, we don't.
So where is your India argument? Where is that?
So actually, okay. So if I consider the graph and take the at first I'm taking the source vertex, then I'm seeing the neighbors of the source vertex, right? So then I'm checking then I'm just checking which one is the shortest one. And the vertex which I want to reach from S, I'm taking the path through each of the neighbors, and then I'm checking whether I'm taking the I'm taking the neighbors, and then I'm checking whether I can reach you, and then I'm taking the minimum.
Yeah, you are just telling me the algorithm. Fine, I understand.
Yeah, but yeah, so
it is not, the proof is not obvious. You should realize that this is proof is not obvious. Because here you are storing at some point of time, you are storing all the minimum distance that uses only the vertices outside Q. And then I'm saying that suddenly if I take the minimum, I end up becoming the shortest distance between S to U, irrespective of whether I am using vertices in the Q or outside of the Q.
Sir, if there are no edges from these vertex outside Q to U, then only we will remove U, right?
No, I'm just remove U by taking the minimum vertex. When did I remove U? Maybe I should go back to this.
Even if there is a edge, then we will compare whether.
No, we are not comparing anything. Let me just try to see if I can go back now.
So when we are removing the first vertex from Q.
Yeah, look at this one. When I'm removing U, U is a vertex with a minimum distance. Remove U. Am I comparing anything?
No, sir, no, sir. But
even in the previous ones, here, at this time, I just told that, okay, C is the minimum. I didn't compare. I just took C because C is the minimum, which is 10. And I'm updating the rest of them. But at that time, when I'm pushing C down goes off. So the top one is Q, top thing is Q. Okay, the top list is Q, the bottom list is outside Q. I'm taking the minimum from the top, which is 10. I'm putting it down and I'm updating the other ones.
Yes.
But at this time, I'm not changing the bottom ones again. Okay. Suddenly, I'm saying is that C is the minimum. Means the C is the minimum, and I am just claiming that 10 is the minimum distance between G to C. At that time, I could have said, okay, now I can take any one of them. I could have taken D. What's the problem? You would not be correct. You realize that,
From
right?
the boundary, we are looking at all the distance and taking the minimum, right?
From the boundary, I'm not doing anything on the, yeah, I mean the boundary, I mean like, yeah. From the boundary, we are taking the
like the shortest,
taking the minimum. But who told us that that boundary
has to be
the minimum? Why can't the path be a much more convoluted path?
Sir, hello.
Yeah.
So when we will try to reach some other vertex, we will have to cover one of the vertices which are there in the neighborhood of the source, right? So that is the reason that. Okay, sorry. No.
Okay. So let me try to give you the proof. You guys are, some of you are getting it somewhat similar to that, but not exactly. Okay. Let me see. Go back again. You can see my screen now again.
Sir, if we have to cross the boundary through other vertices,
Yeah, so let's see. Okay,
then it could have been
okay, so I'm just trying to prove this one. Okay, so consider the time. Okay, so let's see, consider the moment when U is picked from Q and removed. What is it that I know from that time? We know what? We know what?
All the adjacent.
Yes. Distance of U is less than or equal to distance of V for all V in Q at that time. Right? So it is adjacent or not, does not matter. I am taking U, which is the minimum in Q. Basic thing, okay? Good. Now, claim. What is it that I am to claim? I want to claim that distance of U is the shortest distance from S to U, right? But what do we know at that time? We know. What do we know? We know this fact, right? We know this was one fact, important fact that we know. And there's another fact that I know. What is it? We know that distance of U is the shortest distance from S to U via V minus Q. These are the two facts that I know. Right now, what is being stored in my distance? It is this thing. This is from the loop invariant, second loop invariant. And this is from the fact that I have been picked up the minimum one. Okay. And now using these two facts, I want to prove this claim. Okay. Is this clear? Whatever we are doing?
Hello, sir.
Yeah, yeah.
Sir?
Yeah.
So this V minus Q part, this part I'm not able to understand.
Okay. I mean, so this is a loop invariant. We have not proved it yet. Okay. So what is a loop invariant? It's the induction kind of stuff, right? I am saying that this is going to be stored. So so think that till now somebody has come up and guaranteed me that these two are satisfied. Okay. Now I am doing one more loop.
Yes.
Okay. And I have to prove that after that loop, one more loop, these two is still satisfied. Right? Okay. Now what I am going to do, I'm saying that, okay, so let us assume, consider the time when U is being picked up. Before that, I know that this is there, that is given, right? That's a loop invariant. That's the induction hypothesis that is there. And now I say that, okay, now I'm picking the U, which is the minimum one. So irrespective of that, this thing is satisfied because of the loop invariant till now. Is this clear? Surajit? Surajit? Am I audible?
Yes, sir.
Okay. Okay. So now using this
Hello.
two, I want to
Yes, sir.
prove this claim. Okay, so let's see. Now here is the proof. Okay. We prove by in contradiction. Let us say there exists another path from S to U with distance less than dist of U. Okay, fine. I will prove that this cannot happen. Okay. So what is the path? So, okay, if I have to think of it here, okay, so think of it, this is the graph. This is my S, and these are the set of all the vertices that I have already picked up. So this is my, sorry, this is the V minus Q part. At that time, U is somewhere here. This is U. U has a distance, right? So that means there is some path from S to U via this one. So this path, the red path, has the distance of U. But now you are saying that there exists a path, let's say, from S somewhere else. It's a path P. This distance. So what this says is that, what do I know? This path, the red path, the distance is dist of U. The purple path, the distance is something, but that is strictly less than dist of U. Is this possible? Okay, now see. So let the path be here. This is the path, right? There exists a path. Okay. So the path is of the form. How is the path looks like? S equals to say V0, then V1, and it goes on till Vt, which is U, right? Consider the first Vi that is not, that is in Q. So basically says these all of them say V5 up to V5 it is in not in Q, and V6 is in Q. It continues like that, right? It has to be, there has to be such a thing. Why? because S is in V minus Q and U is in Q at that time. So when the loop is starting, so I'm going from V minus Q to Q, and at that time I have this whole thing done, right? And you're saying that, oh, there is a path that uses all of them, crosses V5 to V6 and reaches U, and this distance is less, right? But what is it? What does that mean? That the distance of the path V0, V1 till V6, or in that respect Vi, what is this distance? This distance is strictly less than the distance of this whole path V0 to Vt, which is, I know that, less than the dist of U, right? And what is being stored in dist of V6 at that time? What is dist of V6? Dist of V6 is the distance of the shortest path from S to V6 using vertices in V minus Q, right? Is the shortest path. Now I have given you a path, or V minus, it should not be V6, this is Vi, right? And what is this Vi? I have already given you a path. So that means that dist of Vi must be less than or equal to distance of the path V0 to Vi, because see, V0 to Vi is a path that where everything before V6 Vi is not in Q, and this is the first one that is in Q, right? So this is a path, and this is less than, what is it, something that I know, dist of U, right? But is that possible? So at this time Vi, or in this case V6, this is in Q, this is also in Q. Now you are saying that dist of Vi is less than dist of U. Then how is it possible that I have picked up U, which is less than all of them? So this contradicts this fact, right? And that is why, so this is a contradiction. So if there is a path which is shorter path, in simple language, if there is a path which is shorter than here from S to U than what is being told here, then this path must have crossed over here somewhere. Now consider the vertex that just crossed here. So if this whole path is shorter than this red path, then this path, half of the path must be also be shorter than this path. And in that case, this value, the value of D of this value vertex must be less than D of U. And therefore, I would have picked this vertex and not this vertex when I'm picking up the minimum. Okay. Is this clear?
Yes, sir, it is clear.
By the way, I had asked you guys to go over the book last time. I mean, the reason is that this is actually a slightly complicated algorithm, the correctness of it. And to explain it in an online form is actually more difficult than what you can think it is. So it would have been much better if you had at least got one attempt in trying to understand this correctness of this particular thing. Now, Can somebody now, if you have understood, who told it's clear?
Yes, sir, it's clear.
Avanish, right? Okay.
Yes.
Can you say, are we, are we using the fact that all the age weights are positive somewhere? Are we using the fact that all the age weights are positive?
Yes, sir, we are using the fact because when we are eliminating, then we are considering that this is the shortest and it cannot be shorter than this. Because if there were negative lines, then there could be some other path where we could reach it and through negative paths, and then we could get less than that.
In this
In the process.
argument, where it is that I'm using. See, it is very important when you give a proof and you are saying that something is being used, you have to tell me in the argument where this proof thing is being used.
The long inequality would not have been, would have been altered, right? If it is
Which
negative.
inequality?
There are, can you come back? Distance of V0 up to Vi less than.
Exactly. This inequality, this inequality will be altered, will not be correct. Or in other words, if there is a path from S to U and I take a shorter path, the distance will be smaller. That is because I am assuming that this path doesn't have any negative cycles, negative edges. But if this path has negative edges, it might happen that this path is much bigger than this path. Or this path weight is much bigger than the whole weight of the whole path. It is not happening because I am assuming that all this part of the path only contains positive edges. Okay. Swarnalipa, is this fine?
Yes, sir.
Were you thinking in this line only, or was it like a problem in your
Yeah.
expression?
No. Yeah, sir. Actually, I was thinking like this, but I was not able to tell you, what to say. Yeah.
Okay, so this is basically only the test for this one. Okay, this is only for this first loop invariant. You can also have to argue for the second loop invariant. That now that I have picked up a vertex, so what is it? This is after that I picked up the vertex, which is the minimum among all the elements in Q. Of that vertex is the shortest. For that vertex, I know the short distance. Now I update the rest of them, and why is this getting updated? This part is actually easier, and I'm not going to do it now. I leave it to you guys to go and prove that this will get updated properly. Okay. So the another thing of this particular algorithm that is very important. This is just the correctness of the algorithm. I again request you guys to please go and read a book. Unless you try to put your effort, you will not understand this particular thing. Once you read a book and you ask me questions, I think things will get sorted out much easier. If you don't, then however much I am trying to explain in this online format, I will not be able to explain it. This is not going to happen. Any doubts, any questions on this particular thing at this point? Okay, so if there's no doubts and no questions, let me now ask the next important thing here. Let me just stop this presentation once again, and let me share the screen once again. The other thing. Can you say, so this is the algorithm, right? Now, what is the runtime of this algorithm? Can somebody say it? Can somebody say what is the runtime of this algorithm? Shai, are you there? Sai, are you there?
Hello, yes, sir.
Yeah, can you tell what is the runtime of this algorithm? Monideep Ailani, are you there?
Yes, sir. I am thinking it is order of v square number of vertices v.
Okay, why?
So because to add one vertex, we are making to add one vertex, we need to see which one is the smallest. So for that, we need to check all the vertices that were not in the set that we have added already. And we also have the distances that we have calculated earlier when adding the previous vertex. So I'm thinking the new distances that need to be calculated would be the number of vertices that were not added.
Okay, so you guys you're thinking the right direction somewhat, but not exactly. Okay.
Yes, sir. Yes, sir. Not
so
exactly.
Look at this one. Okay, the distance is being updated. Okay, consider this particular example. Okay, when I'm at E, I'm updating E to B, E to C, E to B, and E to D, right? When I'm C, I'm updating C to B. When I'm up at F, I'm updating F to E and F to D, right? And I'm doing a minimum over all of this kind of stuff. I'm at any point of time, I'm doing, so updating, okay? So for every age, so for every time I am at a particular vertex, okay, every time I'm doing it, like for example here, I have put D in this set. At that time, I am going to do what? I am just going to look at the degree, out degree of D number of elements. Out degree of D number of elements, update them, and updating each of them is just a matter of taking a minimum between two numbers, right? And that's it. So if you took it as a whole, then this whole stuff over here, when you update the distance, that is done once every age. That's it. At most once every age. I will not look at an age between D to E multiple times. I will just look it once when I am updating D or when I am removing D from Q. That's it. So this part is not the problematic part. So this part is just the number of ages, which is E. Okay. The problematic part is somewhere else. The problematic part is that, see, how many times will the loop continue? The loop will continue V number of times, right? Every time you remove one vertex from the queue. Great. Which vertex do you remove? You remove the one which is the smallest vertex. How do you compute the smallest vertex? Every time this computing the smallest vertex will take order of the size of Q, right? So if you think of it, the initially Q is of size n. At that time, to compute the set of to compute the smallest distance is smallest vertex is order n number of steps. Then it is n minus 1. Okay, Q becomes size of n minus 1. Then the now cost of computing the smallest vertex is n minus 1. Then becomes n minus 2, and the cost becomes order of n minus 2. So if you do the backward thing, you will see that the number of steps required in this algorithm is order 1 plus 2 plus 3 plus 4 or till order n or n minus 1. which is order n square or v square. So this algorithm, as has been explained, that has runtime order of v square. Okay. So it takes order of v square, and that's it. Okay. Is it fine? Is it clear?
Yes, sir.
Surajit, is it clear?
Sir, I have to read it.
Very good. Now
I
that
have to
you
go
understand
through
that you
the
have read it.
book, otherwise I'll not understand it completely.
Yeah. Good. So order of A is v square. Now, but
Hello.
there is a yeah. Go ahead.
Sir, if we maintain min heap for dist values,
Yeah. So
then
if you use a kind of a something more more cleverer, okay. See, mean heap is not a easy thing because you have to update various things also, right? It is not just coming up with the removing the mean. You have to remove the mean, and at the same time, you at various times you have to update the various things, right? Update the various elements, but that can be done using what is known as the Fibonacci heap. Now, I am not going to talk to you about what the Fibonacci heap is, but the basic idea is that the Dijkstra's algorithm, the runtime is order v square, but a clever implementation using what is called a Fibonacci heap can reduce the number of steps to v log v, e plus v log v. Okay. And if you guys have done Fibonacci heap, fine. This is not a part of this course, so you don't have to know this one. But what is important for you guys to know is the correctness of the Dijkstra's algorithm and the fact that the Dijkstra's algorithm, at least as normally stated, will take order v square steps. Okay. So this brings us to the end of the Dijkstra's algorithm. The Dijkstra's algorithm is used to compute the distance between single source shortest path, so from one vertex to all the vertices, and it uses the assumption very crucially that all the edge weights are positive. So this is how much it will be there in the midsem. After the midsem, we will be starting from here only, and we will continue with the fact that how much is how can you handle negative edges, negative edge weights, and so on. Okay, so any other questions? Okay, so if there is no other questions, so let's stop the class now, and we will meet again. So we will, of course, I will send you an update about what all things to be done in the midsem, and we will meet in Tuesday. Tuesday from in 2 weeks time. The one thing that I had told you guys in the classroom, that there will be 2 midsems. One midsem will be on next Thursday. The another midsem will be sometime later on. That is mostly as a makeup midsem for those people who have missed this first midsem. And it is expected that whoever is in good health should take this midsem. Now, if you decide that, okay, I will use this ploy of taking the second midsem instead of the first midsem, and in case something happens in the second midsem at that time for you, that time I am not listening to anything. Because the second midsem is particularly for those people who are suffering because of COVID. Either they are suffering themselves or suffering because of some close family members and all going through some COVID related issues and having some tough time because of that. So I'm really banking on your honesty to kind of say that, okay, I am fine now at this time, and I would take the midterm on Thursday. Okay. Okay. So, any questions?
This algorithm is giving us a tree, right? Is it a minimal spanning tree?
No, it is not at all a minimum spanning.
Okay.
It's not a minimum spanning tree under any stretch. Yeah. Okay. Good. Yeah, you can try to come up with an example where this is not the minimum spanning. Okay, so we're good. So with this, I end this class today.
Hello, sir.
Yeah, hi.
Next week, are you going to have class?
No, next week there will be no class. And in fact, next week there should not be of any class of any course. Is there a class? Are there classes in the other courses?
Hello.
Hello, are there classes in other courses next week?
Yeah, information and coding theory classes.
No, you can ask. You can tell him not to do that actually, because that will be. This is a particularly a class kept for the midterm week, midterm evaluation.
Okay, sir.
Yeah, you can say that this is being kept as a midterm evaluation. So it will be more appropriate to not have classes. Okay. Okay.